2.2 Derivatives of Exponential Base E Functions. Southwestern College, Professor Maria Olivas. Section 2.2 Derivatives of Exponential Base E Functions. Objectives: differentiate exponential base E functions, and solve applied problems involving exponential base E functions and their derivatives. First, we need to recognize the difference between a power function and an exponential function, because when we take the derivatives of these two functions, we take them in a different way. So let's start off with talking about a power function. I am going to put a box around the words power function, and I'm going to write down power, underline it twice, and right after that I'm going to write down f of x equals x raised to the n power. So the derivative of that would be f prime of x is equal to n times x raised to the n minus 1 power. So this is a power function. So I have gone ahead and drawn a couple of vertical lines right to the right of the work or the example that I just did for a power function, and I am now going to do an example of an exponential function. I've drawn a box around the word exponential, and I've written down the word exponential underlined twice. So the example I'm going to write down for exponential function is g of x equals e raised to the x power. Notice the difference between the two functions. In f of x equals x to the nth power, the x, or the variable, is in the base, whereas in the exponential function, the x, or the variable, is in the exponent, or in the power. When you have a power function, we're going to use just our regular old power rule for finding derivatives. When we have an exponential function, especially one like this one, an exponential base E function, we need to do this in a slightly different manner. So rather than derive the formula for the derivative of f of x equals e raised to the x power, let's explore some values on our calculator, and by looking at those values, let's try to figure out what the derivative of this function would actually be. So let's go ahead and see the table of values that we're going to be filling in to compare the values between f of x equals e raised to the x and the derivative of f of x equals e raised to the x. Graphing functions. Graph in y1 the function of f of x equals e raised to the x power. Use the calculate feature to complete this table, round to 3 decimal places. Here we see a table with 3 columns. Across the top of the table, for the categories of each one of these columns, we have x for the first column, and this is from left to right. We have x for the first column, e raised to the x power for the second column, and the derivative of e raised to the x for the third column. Under the x column, for our values for x, we have -2, and I'm going from the top to the bottom. We have -2, -1, 0, 1, 2, 3, and 4. And under e to the x and the derivative of e to the x, those values or those spaces are blank because we have not found those values yet. So we are going to find those values using our graphing calculator next. So let's go ahead and move to our graphing calculators so we can input our function that we're trying to find the values to. We're going to press the y equals button first in your graphing calculator. So here on the screen we see the graphing calculator buttons, and I'm pressing the y equals, I'm going second, and I'm pressing the division symbol because e is right above it, and I'm raising that e to the x power. We are going to press zoom and 6 in order to achieve a standard window, and here we see our function f of x equals e raised to the x power displayed on a coordinate plane where the x-axis goes from -10 to 10 and the tick marks are separated by a scale of 1, and the y-axis goes from -10 to 10 where the tick marks are separated by a scale of 1. So now what we're going to do is we are going to graph the derivative of this function. Let's go to y equals. Let's press the down arrow key. And where it says y sub 2, we're going to press math. We're going to press number 8 for n deriv. It's going to give us the derivative. Here we have to put an x for d dx to get the derivative with respect to x. Here inside the parentheses, we need to put down the function. So I'm going to click on vars, the vars button, and I'm going to scroll over to the right where it says y vars, and I'm going to click on number 1, y sub 1, and then by pressing enter on y sub 1, that's going to input the function that I have already for y sub 1. And then here it's going to say such that x is equal to x, and that's going to provide me the derivative of my function f of x equals e raised to the x. Let's go ahead and press graph. If you notice, there is a function that seems to be traced right over our original function. If we go to second table, we're going to notice that the values here are exactly the same in both columns. There is nothing that seems to be different here. So what does this tell us? This tells us that our derivative of our function is going to be exactly the same as our original function. So the derivative of f of x is equal to e to the x is going to be f prime of x is equal to e to the x. Let's go ahead and type in these values, or I should say write in these values into our table of values that we have here. So let's go ahead and start here where it says the column e raised to the x power. In that first spot, right next to the x value where x is equal to -2, let's go ahead and write in our first value what the value of our function was at x equal to -2. That's going to be 0.135. And we're rounding to 3 decimal places. Now the value of f of x is equal to e to the x when x is equal to -1 is 0.368. When x is equal to 0, it's 1. When x is equal to 1, it's 2.718. When x is equal to 2, it's 7.389. When x is equal to 3, it's 20.086. And when x is equal to 4, it's 54.598. Now let's write down the values for the derivative of e to the x. When x is equal to -2, it's 0.135. When x is equal to -1, it's 0.368. When x is equal to 0, it's 1. When x is equal to 1, it's 2.718. When x is equal to 2, it's 7.389. When x is equal to 3, it's 20.086. And when x is equal to 4, it's 54.598. The values are exactly the same. So based off of this observation, what should we write down here for our new formulas? We should write down that the derivative with respect to x of, open up a set of parentheses, e to the x, close the parentheses, is going to be equal to simply e to the x. I'm going to draw a vertical line here to separate this formula from this new formula I'm writing right here. It's very similar. The derivative with respect to x of, open up a set of parentheses, e to the u power, close the parentheses, is going to be equal to e raised to the u power times du. So these are going to be our formulas for when we're working with our exponential functions with base e. Examples: differentiate each function. Number 7. F of x equals e raised to the 4x power. I'm drawing an arrow pointing at the 4x in the exponent. We're going to set u equal to 4x. So that means du dx will be equal to 4. So that means that the derivative of u with respect to x is going to be equal to 4. F prime of x is equal to e raised to the 4x power times 4, which equals 4e raised to the 4x power. We're going to box that in, and that's going to be our answer. That's going to be our derivative for that function. Number 8, y equals e raised to the -6t squared power all over 2. So that's going to be equal to 1/2 times e raised to the negative 6t squared power. So the derivative of y with respect to t is going to be equal to 1/2 e raised to the negative 6t squared power. I'm going to highlight in yellow the negative 6t squared power. And now we need to take the derivative of that. So that's going to be negative 12t, right? We're taking the derivative of that power with respect to t. So the derivative of y with respect to t, or dy dt, is equal to negative 12 over 2 times t e raised to the negative 6t squared power. And this will equal negative 6te raised to the negative 6t squared power. I'm going to go ahead and box that answer in. That's going to be our derivative for this function. And now we can go on to number 9. Number 9 says y equals x squared times e raised to the x power. So for this particular problem, we're going to need to use the product rule because we do have a product here between x squared and e raised to the x. If you recall, the product rule states u dv plus v du. I'm going to label x squared as u, and I'm going to label e raised to the x as v. Therefore, y prime is equal to e raised to the x power times, open up a set of parentheses, 2x, close the parentheses, plus x squared times, open up a set of parentheses, e raised to the x, and close the parentheses. Y prime equals 2x e raised to the x plus x squared times e raised to the x power. So for y prime here, this is going to be equal to, I can factor out that x e raised to the x power, and then that's going to get multiplied with, we're going to open up a set of parentheses, 2 plus x, close the parentheses. I'm going to box in the last 2 rows here for my answers because you could write the answer either way here, and that would be fine. Number 10. Y equals e raised to the 2x power all over x cubed. This is going to require the quotient rule. So if you recall, the quotient rule was v du minus u dv all over v squared. I'm going to label my numerator as u and my denominator as v. I'm circling the numerator, the e raised to the 2x, because that represents my u. So that's going to be dy dx, or the derivative of y with respect to x, is equal to, open up a set of parentheses, x raised to the 3rd power, close the parentheses, times, open up a set of parentheses, e raised to the 2x power, and then times 2, close the parentheses, minus, open up a set of parentheses, e raised to the 2x power, close the parentheses, times, open up a set of parentheses, 3 times x squared, close the parentheses, all over x raised to the 3rd power inside a set of parentheses, and we're going to square that. So now we're going to have dy dx is equal to 2x raised to the 3rd power times e raised to the 2x power minus 3x squared times e raised to the 2x power all over x raised to the 6th power. So dy dx equals, here what we're going to have to focus on is the e raised to the 2x. So I'm going to notice that they both have e raised to the 2x here as a common factor, and I'm also noticing they both have an x factor. The smaller power on the x is the 2nd power. That's the smaller one, so I'm circling it and writing the word smaller next to that exponent of 2. So that's what I'm going to factor out. I'm going to factor out an x squared times e raised to the 2x. So dy dx equals x squared times e raised to the 2x times, open up a set of parentheses, 2x minus 3, close the parentheses, all over x raised to the 6th power. I'm highlighting the x squared that's in the numerator and the x to the 6th that's in the denominator. Because we have a common factor here in the numerator and denominator, we can divide out a common factor of x squared and reduce this and simplify it a little further. dy dx equals e raised to the 2x power times, open up a set of parentheses, 2x minus 3, close the parentheses, all over x raised to the 4th power. And that's going to be our final answer, so we're going to box that in. I'm pointing an arrow on the right hand side of this, and this I'm writing next to the arrow, I'm writing lowest terms. So this would be the answer written in lowest terms. No common factors in the numerator and the denominator. Example 11. Write the equation of the line tangent to the curve f of x equals e raised to the negative 2x power when x equals 0. So in order to write the equation of a line that's tangent to the curve, we need to find the derivative in order to find the slope at that tangent line. And we need a point. So f of x equals e raised to the negative 2x power. So f prime of x equals negative 2 times e raised to the negative 2x power. F prime of 0, which will provide us the slope, is going to be equal to negative 2 times e raised to the negative 2 times 0 power. F prime of 0 equals negative 2 times e raised to the 0 power. So f prime of 0 is equal to negative 2, because negative 2 times e to the 0 is equal to negative 2 times 1. I'm going to draw a vertical line here to separate the work that I did here on the left-hand side from the work that I'm doing on the right-hand side. Now I'm going to write down the point that I need here. The point is going to be equal to the ordered pair 0, f of 0. In order to find f of 0, we need to substitute 0 back into the original function. So f of 0 is equal to f of 0 is equal to e raised to the negative 2 times 0 power, which is equal to 1. Our point is going to be at 0, 1. 0 is going to represent x sub 1, 1 is going to represent our y sub 1. And now we just substitute into point slope form, which is y minus y sub 1 equals m times the quantity x minus x sub 1. So now when we substitute, we get y equals now after substitution, we get y minus 1 equals negative 2 times the quantity x minus 0. Y minus 1 equals negative 2x, and if I add 1 to both sides to isolate the y and write this in slope-intercept form, I will get y equals negative 2x plus 1. So my answer in slope-intercept form will be that y equals negative 2x plus 1, so we're going to go ahead and box in that answer. Example 12. The daily output of a worker tends to increase over time. Suppose a company determines that after T working days, the daily output of items produced by the average worker can be modeled by N of T equals 80 minus 60E raised to the negative 1200th T power. A. Evaluate N of 10 and N of 30. Interpret your results. So let's start off with just the A part before I read the B and C. I'm going to put a cloud around the function N of T equals 80 minus 60 times E raised to the negative 1200th T power. I'm going to go ahead and substitute 10 for T. So N of 10 is equal to 80 minus 60 E raised to the negative 1200th times 10 power. N of 10 is approximately equal to 61.928 thousandths items. So N of 30 is going to be equal to 80 minus 60 E raised to the negative 1200th power times 30. So N of 30 is approximately equal to 78.3 0.361 items. Now we need to interpret our results. First, let me lasso in all the work I did for part A, and I'm going to shrink it towards the left-hand side to give me a little bit more space. And now I'm going to write down how I'm interpreting my results on the bottom here. So if we interpret our results, this means that the output is increasing with more days. So the more days go by, the more our output is going to increase. So output is increasing with more days on the job. I'm going to go ahead and box in that answer, and I also drew a vertical line here separating the two problems I did here where I evaluated n of 10 and n of 30. And I also boxed in those values that I attained when I evaluated n of 10 and n of 30. B, find n prime of t. N prime of t is equal to negative 60e raised to the negative 1200ths t power times, and here we're going to have negative 1200ths. I have an arrow here pointing to the right, so this is going to turn into n prime of t equals 7.2e raised to the negative 1200ths t power. That's going to be our derivative. I'm going to box that in. Now, I have here the derivative written as n prime of t, but that is not the only way we could write this derivative. Remember that we could also write this as dn dt, the derivative of n with respect to t. So I'm just going to go ahead and draw a little arrow pointing down from the n prime of t, pointing down to dn dt. Now with the derivative, we're going to be able to find that rate of change that's occurring at each one of these, at n prime of 10 and n prime of 20 and n prime of 30. C, evaluate n prime of 10, n prime of 20, and n prime of 30. Interpret your results. N prime of 10 is going to be equal to 7.2e raised to the negative 1200ths times 10 power, which is approximately equal to 2.169 units per day. So this represents our rate at t equal to 10. N prime of 20 is equal to 7.2 times e raised to the negative 1200ths times 20 power, which is going to be approximately equal to 0.653 units per day. And n prime of 30 equals 7.2 times e raised to the negative 1200ths times 30 power, which is going to be approximately equal to 0.197 units per day. So looking over these rates of change appear to be decreasing. Although n is increasing with the higher amount of working days, the units per day that are being created are decreasing. So n is increasing at a decreasing rate. So let's go ahead and box in our answers for these. We're going to box in each one of those values that we got when we evaluated n prime of 10, n prime of 20, and n prime of 30. And we're also going to box in our interpretation of the results, which was n is increasing at a decreasing rate. All right, let's go on, and we're going to move on to part C, where we need to find n double prime of t, the second derivative of n. So n double prime of t is going to be equal to 7.2 times e raised to the negative 1200ths times t times negative 1200ths. And this is going to be equal to negative 0.864 times e raised to the negative 1200ths t power. And I'm just going to go ahead and rewrite that as n double prime of t equals negative 0.864 e raised to the negative 1200 t power, and box that in. That represents my second derivative. And as you can see, this is going to provide me with negative values. If I were to substitute values from that were, say, positive from quadrant 1, it's going to give me negative values, which means my graph of n is going to be concave down, which further reaffirms the fact that n is increasing at a decreasing rate. All right, let's go on to part D. Part D states, sketch the graph of n and think about the relationship between the shape of the graph and the results you obtained in part C. I'm going to go ahead and draw a coordinate plane here. I'm going to draw the vertical axis first, which is going to represent our n of t. And I'm going to draw a horizontal axis, which is going to represent t, the number of working days. N of t represents the daily output of items produced by the average worker. I'm going to go ahead and draw some tick marks. Let's start off with drawing tick marks on the horizontal axis. I'm going to separate these tick marks. They're going to be separated by a scale of 5. We're going to go from 0 to 30. And then I'm going to draw tick marks on our vertical axis. These tick marks are going to be separated by a scale of 10. And we're going to go from 0 to 80. So we're going to need some ordered pairs in order to help us plot this graph. But before we do that, I'm going to find the limit as t goes to infinity of this function, which is, we're going to open up a set of parentheses here, 80 minus 60 e raised to the negative 0.12 t power, and then close the parentheses. And we want to know this because we want to know what the behavior is of the function as t gets very large. I'm going to rewrite a part of this function here. I've highlighted the part that says 60e raised to the negative 0.12t in yellow, and I'm rewriting it without a negative exponent. So it's going to be rewritten here as 60 over e raised to the 0.12t power. Now as t gets very large, this fraction here is going to go to 0. So in reality, this limit as t goes to infinity of this function is going to be equal to 80. So I'm going to draw a dashed line, a dashed horizontal line at n of t equal to 80, because I know that my function is going to get very, very close to this line, but it's never going to be equal to it, and it's never going to pass it or go above it. I'm going to now draw a 2-column chart, or 2-column table, in order to come up with some ordered pairs. The first column is going to represent values of t, and my second column is going to represent values of n of t. Let's start off with t equal to 0, and then we'll do t equal to 10, and then we'll do t equal to 30. So let's start off by substituting 0 into our function for t, and let's see what n of t is going to be equal to, or I should say n of 0. N of 0 is going to be equal to, well, first let me rewrite my function so I remember what my function was. N of t is equal to 80 minus 60 e raised to the negative 0.12 t power. So n of 0 is equal to 80 minus 60 times e raised to the negative 0.12 times 0 power. N of 0 is equal to 80 minus 60 times e to the 0 power. N of 0 is equal to 80 minus 60, so that's just going to be equal to 20. So 0, 20 is going to be that first ordered pair that I have here to plot on my graph. And the next one is going to be 10, 61.928, and the last one 30, 78.361. And I already had these values from the previous parts that I had done to this problem, so I didn't have to find those values. I'm going to go ahead and take the work I did here for my n of 0, and I'm going to lasso it and shrink it and move it to the right so that I have more space in order to draw my graph. So now that I've moved that work over to the right, I've got plenty of space here to sketch my graph of n. I've plotted the point 0, 20. Now I'm going to plot the point 10, 61.928 to right about here. And now I'm going to plot the point 30, 78.361. So starting at 0, 20, I'm going to draw a curve that goes upwards, and it gets very close to the line at n of t equal to 80, and it just kind of curves alongside it but doesn't touch that line. I'm going to label my ordered pairs, and now I've labeled each one of those ordered pairs, and I have drawn my sketch for my graph. So you can see here that this graph is increasing, so I'm going to write down the word increasing right above, curving alongside the function that I drew here on the graph. You can also see that this graph is concave down, so I'm going to write down the words concave down underneath the graph. I'm going to underline those words. And this is exactly what we had already been imagining based off of all the work we've been doing. Yes, the daily output of items has been increasing as the number of days increase, but the rate at which it was increasing was decreasing. So that's exactly what our graph represents. Example 13. The total cost of operations in millions of dollars for a car company is given by C of t is equal to 150 minus 80e raised to the negative 0.5 t power, where t represents the number of years since the company was founded. A. Sketch a graph of this function from t equal to 0 to t equal to 10. I'm going to start off by highlighting some key information. I'm going to highlight where it says total cost of operations in millions of dollars in yellow. I'm going to highlight the function in green, C of t is equal to 150 minus 80e raised to the negative 0.5 t power. And I'm going to highlight in blue where it says t represents the number of years since the company was founded. I'm also going to circle for part A where it says t equal to 0 and t equal to 10 because that's where I need to sketch my graph from those values. I'm going to go ahead and draw a coordinate plane here with a vertical axis and a horizontal axis. I'm going to label these axes. The horizontal axis is going to represent t in years, and C of t is going to be the vertical axis, which is going to represent the total cost of operations in millions of dollars. Next, we're going to draw some tick marks here for the axes. Let's start off labeling 0, the origin, and then I'm going to go ahead and label these tick marks here for the horizontal axis. I'm going to go by scale of 1. So it's going to go from 0 all the way up to 10. Because remember, it did say sketch a graph for this function from t equal to 0 to t equal to 10. Now for the vertical axis, I'm going to go ahead and draw some tick marks on that as well. Looking at the function, C of t is equal to 150 minus 80e raised to the negative 0.5 t power. I need to look at that in order to determine how high up I need to go in terms of my values for C of t. I'm going to write out here the limit as t approaches infinity of, open up a set of parentheses, 150 minus 80e raised to the negative 0.5 t power, close the parentheses. I'm going to highlight the 80e raised to the negative 0.5 t power, and I'm going to put a cloud around it and draw an arrow going down, and I'm going to write a 0 below it because that's what this is going to go to if t goes to infinity. And we discussed this in the last problem that we just did. So this is going to go to 0, and the only thing this is going to be equal to is 150. Before I draw that dashed horizontal line, let me first label my tick marks for the vertical axis. I'm going by a scale of 10 from 0 to 150. I'm also going to draw a 2-column table or 2-column chart where I'm going to label it with the first column representing t, the first column, that means the column on the left, and the second column on the right is going to represent C of t. I'm going to choose 0 for my first value of t. So I'm going to substitute 0 in place of my function. C of 0 is equal to 150 minus 80 times e raised to the negative 0.5 times 0 power. C of 0 equals 150 minus 80 times e raised to the 0 power. C of 0 equals 150 minus 80 times 1, and C of 0 equals 150 minus 80, which is equal to 70. So my first ordered pair that I came up with is going to be 0, 70. I'm going to take the work that I just did for C of 0, I'm going to lasso it, I'm going to shrink it, and I'm going to move it over to the right-hand side because I don't really need that work anymore. I need the space here where I was doing that work to draw my graph. So now that we move the work over to the right, I can now finish sketching my graph for this function. Okay, I'm going to go ahead and choose a few more values for t to come up with some ordered pairs to help me sketch the graph of this function. We're going to choose t equal to 2, and we're going to choose t equal to 7. C of 2 is going to be approximately equal to 120.57. I did that on my calculator, so you guys could just go ahead and plug that into your calculator. And I'm going to round that to 120.6 in the table to use that as the ordered pair to make it easier to plot. C of 7 is approximately 147.58, and I'm going to round that to 147.6. Now that I have those values, those ordered pairs, I can now go ahead and begin sketching my graph of my function. I'm going to start off by drawing that horizontal dashed line that represents my asymptote, my horizontal asymptote. So it's going to help guide me when I'm sketching my graph. I labeled here the point 0, 70 and the point 2, 120.6, and the last point I have here is going to be 7, 147.6. Starting from the 0, 70, I've started drawing my curve going upwards and then just kind of lining up there with my horizontal asymptote, never touching the horizontal asymptote, never passing it. I've labeled my points with the ordered pairs, with the corresponding ordered pairs for each of those points. And I have my sketch of my graph. This graph represents C of t. Okay, part B. Find the marginal cost C prime of t. So let's go ahead and find the derivative of C of t. So C prime of t is going to be equal to negative 80 times, open up a set of parentheses, e raised to the negative 0.5 t power, close the parentheses, and then times negative 0.5. C prime of t is equal to 40 times e raised to the negative 0.5 t power. And I'm going to box that in because that represents my marginal cost. That's the derivative of C of t. Part C, evaluate C prime of 2 and C prime of 5. Round each answer to 3 decimal places and put units on your answers. C prime of 2 is equal to 40e raised to the negative 0.5 times 2 power, which is going to be approximately equal to 14.715. And this represents millions of dollars per year. So it would be $14 million or $14,715,000 per year. C prime of 5 equals 40 times e raised to the negative 0.5 times 5 power, which is approximately equal to 3.283 millions of dollars per year. I'm going to go ahead and box in my 2 answers here that I got when I evaluated C prime of 2 and C prime of 5. Now, part D says, explain what C prime of 2 represents. C prime of t represents marginal cost, and marginal cost is the change in the total cost that arises when the quantity is incremented by 1 unit. Since t represents years, and we're looking for C prime of 2, this represents the approximate cost in year 3. It's year 3 because that would be 1 more unit greater than 2. Now let's box that in. Part E. Find the limit as t goes to infinity of C of t and explain what it represents. So we already did this actually, but we'll do it again right here. Limit as t approaches or t goes to infinity of, open up a set of parentheses, 150 minus 80 times e raised to the negative 0.5 t power, and close the parentheses. And this is going to be equal to $150 million. So if you recall in the graph, that 150 C of t value represented the limit, or where the function was not allowed to reach that value or go above that value. So it's kind of the value where the cost leveled off, and it also was limited to not equal that amount. So it seems that the total cost levels off at no more than $150 million per year. So that's our answer for that problem. All right, let's go ahead and box that in.